In this lesson, we're going to talk about the bisectors in triangles. The objective is to identify properties of perpendicular bisectors and angle bisectors. And these are going to be points of concurrency in a triangle. There are 4 different points of concurrency. We've already learned about 2 of them in previous lessons. We learned that medians go from a vertex to the midpoint of the opposite side, and where all of the medians come together inside a triangle is called a centroid. That was one point of concurrency we learned about. And the other is with altitudes. An altitude goes from a vertex perpendicular to the opposite side, and where all 3 of the altitudes of a triangle meet is called the orthocenter. We learned about that in a previous lesson. So now we're going to pick up the other 2 points of concurrency. So just as a refresher, when 3 or more lines intersect at one point, that's called concurrent. They're concurrent, and the point at which they intersect is the point of concurrency. So we learned that with the centroid and the orthocenter when we learned about them. So now let's look at our next theorem that we're going to learn about concurrency of perpendicular bisectors. So the concurrency of perpendicular bisectors theorem says that the perpendicular bisectors of the sides of a triangle are concurrent at a point that is equidistant from the vertices. So here in this diagram, we have perpendicular bisectors that are PX, PY, and PZ, because they're all perpendicular bisectors of the sides of the triangle. And they're all concurrent at point P, that point in the center. So the distance between, so what this is saying is that from that point in the center, point P, front to each vertex, so from P to A, from P to B, and from P to C, those are all congruent segments. So they're equidistant from the vertices. So the point of concurrency of the perpendicular bisectors, that point P in the center, where they all meet, is called the circumcenter. It's the circumcenter of that triangle. And it's called a circumcenter because if you have, there's a circle, if you circumscribe a circle is circumscribed, let me spell that right, circumscribed about a triangle. If the circumcenter of the triangle, so if let me try to show you what it would look like. If I circumscribed a circle around that triangle, which means it only goes through the vertices of the triangle. There's a circle that goes through each vertex of the triangle. Then these distances from the circumcenter to that vertex is going to be a radius of that circle. And the radii of circles are all congruent, so that's why that distance is equal between PA, PB, and PC. So let's look at our next theorem. The next theorem is about the concurrency of angle bisectors theorem. So the bisectors of the angles of a triangle are concurrent, which means they all meet together at a point that's equidistant from the sides of a triangle. So in this diagram, we have angle bisectors, and you can tell they're angle bisectors because if you look between B and P here, that they're marked congruent, the angles where it's bisected, and then between A and P there's a difference congruence marking there. There's a 2 congruence marking to show those are congruent, and between P and C there's a 3 congruence marking to show that those 2 are congruent. That's how you know that they're angle bisectors. So you have the angle bisectors, and so from that point P, they're concurrent at point P, and the segments that are going to be congruent are the distance from that point perpendicular to the side between P. So it would be PY, PX, and PZ. Those segments are all going to be congruent because that, and let's look at the next definition. The point of concurrency of the angle bisectors is called the end center of the triangle. For any triangle, the end center is always going to be inside the triangle because it is, the end center is the center of the circle that is inscribed in the triangle. So let's look and see, let's inscribe the circle that's going, if you inscribe the circle inside there, each one of those segment lengths between PX, PY, and PZ, those are all congruent segments because they're radii of that inscribed circle. So let's look at the examples. In problem 1, we're finding the circumcenter of this triangle. It says, what is the center of the circle that you can circumscribe about a triangle whose vertices are, let's plot these. A is 0,4. B is 0, 0. And then C is 8, 0. So let's draw this triangle. So we want to know this, what is the center of the circle that you can circumscribe about that triangle. So that is the definition of it, of the circumcenter. The circumcenter of that triangle is going to be where the perpendicular bisectors of each of the sides meets. Since this is a right triangle, that makes it a little easier on us because it's easier to find the perpendicular bisector. Let's look between A and B. Between A and B, it's a vertical side and it's a side of length 4. So the perpendicular bisector is going to be, it's going to go through 2, and it's going to be another, it's going to be that horizontal line there that goes through 0, 2. Now let's look at the bottom of the triangle, which is a horizontal line between B and C. It goes from the origin to 8, so it's a length of 8. So the perpendicular bisector for that side is going to be at 4, and it's going to go vertically. So we have 2 of the perpendicular bisectors, and that's really all we need to see where they meet. And they meet on the triangle, and the point where they meet is the point 4, 2. So that is the circumcenter for the circle that can be circumscribed. Okay, so once again, think about what circle can be circumscribed about this triangle. and you can kind of visualize that that's going to be the center of the circle that's around that, circumscribed about that triangle. So let's go on to the next problem. So in problem 2, you're using a circumcenter to answer this question. A civil engineer wants to install a cell phone tower that is equidistant from the mall, the airport, and the subway. So how should the civil engineer determine where to build the tower? So you just need to explain how a civil engineer would do this. So if you look at the triangle that's formed by these 3 points, what does the civil engineer need to do to find a point that's equidistant from the mall, the airport, and the subway? So just by definition over here, the definitions and theorems we've gone through of a circumcenter, he needs to find the circumcenter of the triangle formed by these 3 points, because the circumcenter by definition is equidistant from each vertex. So just write that explanation, okay, that you're going to find the circumcenter of the triangle formed by the mall, airport, and subway. Because the circumcenter is equidistant from each vertex. So let's go on to look at problem 3. In problem 3, we're going to identify and use the end center of a triangle. So that's the point where all of the angle bisectors are meeting. Here it says GB is 8x minus 7, and GD is 5x minus 8. And so the question is, what is the length of GF? So by definition, we can see that these are angle bisectors because of the congruence markings marked on the angles in the triangle. These are angle bisectors that are meeting at an end center. And so all of the segments formed from the end center perpendicular to each side have to be congruent by this theorem that we've gone through. So what is GF? You're going to set GB equal to GD first, since those are the ones you have values for, to find the value of x, which you have 8x minus 7 is equal to 5x plus 8. Subtract the 5x from both sides, gets you 3x. Add the 7 to both sides, gets you 15. X is 5. So we need to plug that back in to find the length of GF, because GB is equal to GD is equal to GF. So we can plug it into any one of these. So GD, let's find the length of GD, is 5x plus 8, which is 5 times 5 plus 8. So 25 plus 8 is 33. So we know that GB equals GD equals GF. They're all congruent. So GF is equal to 33.